In the previous lecture, we have talked about one of the technique, the first technique for transformation of the random variable, and that technique was basically nothing but we try to find out the cumulative distribution function of y, which is g of x, given the distribution function of x. Now, in this particular lecture, we are going to talk about the second technique, and as we proceed, you will see that second technique is different for discrete random variable and continuous random variable. So, the second technique, what we try to do is that we are trying to find out the probability mass function of y if y is discrete, or probability density function of y if y is continuous. Of course, once we get the cumulative distribution function using the last technique, using the previous technique, we can able to find out the probability mass function or probability density function based on whether the corresponding random variable is discrete or continuous. Even the previous technique can be used for neither discrete nor continuous kind of random variables. But this technique, as we proceed, we will see that this technique can be used either for the discrete random variable or for the continuous random variable. And not only that, we have to use this technique in a different way for two different kind of random variables. Okay. So here our aim is to find out the probability mass function or probability density function of y without finding the cumulative distribution function of y. So it is the direct, we will try to find out the PMF or PDF directly. Okay, so let us start with example, because at least for the discrete case, the example is most easier way to understand this technique. So this this particular thing we have already considered in the when we discussed the technique one. So same random variable, same discrete random variable x having same PMF, this thing, and same transformation y equals to x square as we have used earlier. Okay, so in that case we try to find out what is the cumulative distribution function of y. Now, without finding the cumulative distribution function of y, we will directly try to find out what is the probability mass function of y. Why I am talking about probability mass function? Let us I'll come one by one. First, notice that the support of x is nothing but -2, -1, 0, 1, 2, and 3. Okay, so x is a discrete random variable and support is basically a finite set. It's finite set. Now, when x is discrete, intuition says that y should be discrete because y should take one of the values 0, 1, 4, or 9. Okay, so we will start with this intuition that y will take any one of the value with positive probability. Y will take with positive probability any one of the values in the set D, which is 0, 1, 4, or 9. So we'll start with this intuition and we'll try to find out what is the probability that y equals to y for each value of y in the set D, and then we try to check if the sum of those probabilities is 1 or not. If this equals 1, we'll say this y is discrete, I am done. If not, then obviously we have to do something else. And fortunately enough, we will actually able to show that the sum is 1, so the random variable will be a discrete random variable. Okay, let us try to calculate the probabilities one by one. So first try to find out what is the probability that y equals to 0. Now notice that y equals to 0 occurs if and only if x equals to 0 occurs. Okay, so y equals to 0 and x equals to 0, these two sets are a kind of equal set, equivalent set. So that's why I can take the probability, I can write the probability y equals to 0 as same as the probability x equals to 0, and that probability from this PDF is 1 by 7. Sorry, this PMF is 1 by 7. Talk about the second one, y equals to 1, and when y equals to 1, this is if and only if x equals to 1 or x equals to -1. And now I know what is the probability of x equals to 1 and x equals to -1. X equals to -1 and x equals to 1. Both of them are 1 by 7. So this probability turns out to be 1 by 7 plus 1 by 7 equals to 2 by 7. Same way I can able to do for y equals to 4, because y equals to 4 happens if and only if x equals to 2 or x equals to -2 occurs. And so that probability is nothing but x equals to 2 is 3 by 14 and x equals to minus 2 is 1 by 7. So this probability is nothing but 3 by 14 plus 1 over 7. And that's going to give us 5 over 14. Okay. Let us talk about the last one, y equals to 9 and y equals to 9 if and only if x equals to 3 or x equals to minus 3, and in this case this probability turns out to be 3 by 4. The reason is nothing but at x equals to 3 the probability is 3 by 4, but x equals to minus 3 the probability is 0. Okay, x equals to minus 3 the probability is 0. So that's why basically we have that probability y equals to 9 equals to 3 by 14. Okay, so what we did, just let us discuss what we did briefly. That we try to find out probability of y equals to y. What we did is that we see this for a particular value of small y, we see this set, and then basically probability y equals to y is same as probability x belongs to this a y, because clearly what is this set? This set is basically collection of all real numbers such that gx equals to y. In our case gx equals to x square, so x square equals to y. Okay, clear? So that means basically we did this way, that probability y equals to y, we write its probability x belongs to ay, and from that we find out what is the probability of x belongs to ay, because we know the probability mass function of x. So notice one thing, at least for this example, see this minus 3 we do not need to consider here, because the probability as minus 3 equals to 0. Probability x equals to minus 3 equals to 0. So what does this mean? This basically means that even I do not need to take this ay set, I do not need to consider all x belongs to R such that x square equals to y. I only need to consider those x which belongs to the support of x and x square equals to y. So we can take, actually what I try to mean is that I can take only this set. I can take only this set, and I can write probability y equals to probability x belongs to ay, and notice that in ay I take only those points which belongs to sx instead of taking those points which belongs to R. Here we are taking those points which belongs to sx, and obviously x square equals to y, and in general gx equals to y. Okay, and in this case it is very easily you can check that 3 by 14 plus 5 by 14 plus 2 over 7 plus 1 over 7, that going to give me 1. If I add this thing, this give us 1. So clearly y is a discrete random variable in this case, and the probability mass function of y is given by this expression. Okay, so in this case, given a probability mass function and given a function, we basically show that in this case the y is a discrete random variable. Not only that, we have shown that what is the probability, we have find what is the probability mass function of y. And the basic idea again is the same. We will first need to guess what should be the support of y, and once we guess that, we need to find out what is the probability y equals to y for each y belongs to the support of y. And then to find out probability y equals to y, we use the inverse mapping thing. We find out what is the inverse image of y equals to y in the support of x, and from that we can find out what is the probability. Okay, so whatever discussed here, that is summarized into the theorem 2.7, and this theorem says that let x be a discrete random variable with probability mass function fx and support sx. And now if I have a function g from R to R, and if we take y equals to g of x, then y has to be a discrete random variable. Only choice is that y is a discrete random variable, and support of y is given by this set. Exactly same thing we did in the last case. And then the probability mass function of y is actually given by this. Notice that what is this quantity? This quantity is nothing but probability x, capital X belongs to the set ay. That is exactly we did in the previous example. Okay, and this particular proof of this particular theorem exactly same as what we have discussed in the previous example. So the exact proof I am not going into. The proof is given here. Please see it. If you have any difficulty, let us discuss it during the doubt clearing session. Okay. But take the main point from here. If x is discrete, and if I take any transformation of a discrete random variable, it will be discrete, and I can find out the probability mass function very easily from the probability mass function of x. Okay, let us take another example. Another simple example, which is basically binomial. X follows binomial, so x is a discrete random variable, and we are talking about y equals to n minus x. So g function is n minus x. First, going into the mathematical thing, first notice that what is y. So what is x? X is basically nothing but number of successes out of n trials. What is y? Y is nothing but number of tosses or number of trials minus number of successes. So clearly y is number of failures. Now if I talk about number of failures, the basic thing of the binomial distribution, the generation of the binomial distribution says that should be again binomial. Y should be again binomial, and number of trials remain same, which is n. So first parameter will remain same, but the second parameter will be now the probability of failure, and the probability of failure is 1 minus p. So this logic tells us that y should be again a binomial distribution with parameter n and 1 minus p. So let us test if we get the same thing or not, and actually we are going to get the same thing. So in this case, what I have to do first, our support of x is nothing but 0, 1 up to n. Now what is the support of y? Support of y is basically n minus each point in the support of x. So n minus 0 give me n minus 2 give n minus 1 give me n minus 1, and so on and so forth. Finally n minus 0 will n minus n will give me 0. Okay, so basically support of x and support of y are same. Okay, now for each y belongs to ay, what is the set ay? Notice that the set ay is basically nothing but the point in the support of x such that gx equals to y, gx equals to small y. Okay, so now if I take y belongs to sy, one point from here, and then basically inverse point is nothing but only one point is there, because this is a linear function, and that point is n minus small y. So in this case the computation is quite simple. Now if I use this theorem directly, basically this set has only one point, is a singleton set, so this sum will not have any effect, only one. The PMF at one point we need to consider here, and when we consider that, we get that it turns out to be PMF of x at the point n minus y, at the point n minus y, if y is one of the point in this support and 0 otherwise. Now plug in the probability mass function of binomial NP distribution, which is NCX. X is replaced by n minus y, p to the power x, x is replaced by n minus y, 1 minus p whole to the power n minus x, again n minus x, x is replaced by n minus y. Okay, and simplify, we get this one, and this is exactly the PMF of the binomial distribution with parameter n and 1 minus p. Okay, so that's what we get, which we should get. Actually the other logic also tells that this should be the distribution of y, and using this particular transformation technique we have shown that we get the same thing. I stop here for this lecture. In the next lecture we will see how to do the same kind of thing with the continuous random variable. Thank you for listening.